from high university, away from administrative thing and just doing physics. The title is a mouthful, but I thought I put that mouthful all here so that I can dissect it piece by piece. At the beginning, I would like to thank my collaborators over time who were participating in that work. It's Matt Burrows, who has now a job in machine learning and AI, Robert Baker, who is in Homeland Security, Steve Webner, Peter Maris, and Christina Launey. So let's get into kind of the warm feeling slides. Basically, what we all want to know and understand exotic nuclei. And basically, there is a whole bunch of interesting things. However, this here is the circle where the regime of no-core shell model, symmetry-adapted no-core shell model resides. And we're pushing here the limits to go out to further. Basically, the original no-core shell model relies on the biggest computer to diagonalize the Hamiltonian. Oxygen 16 still has a reasonable modest model space. Peter Maris did calcium-48 now, but the model space is relatively small. The symmetry adapted tries what Grigor tries to use symmetry methods to take irreps and capture the most important structure of the nucleus. So what do we learn? How do we learn most about the nuclei? It's about in reactions. Elastic scattering has been traditionally used to extract optical potential RMSA radii density distributions. And I always like to show here one of the seminal publications which found out the beta distribution helium-6, helium-8, that those nuclei are much larger than you would think about. So let's go. Exotic nuclei are short-lived, so you cannot prepare them in an initial state. So what you do is inverse kinematics, and that may have its own challenges where I come to. And the other challenge for theory is that in the continuum, you can only solve the few body problem exactly. And few body is a definition of time. It's now Livermore, they're solving the 5-6 body problem exactly. But in the end, if you want to go to heavier nuclei, you always have to cook the many body problem down to a few body problem. And for example, since I'm here in the realm of Philomena, if you have a DP reaction, you cannot do this thing. You have the deuteron and you have the nucleus as a blob. It can be a modified blob with some core excitation, but it still is a blob. And so then you write down the Hamiltonian for the effective few body problem. And we all believe that we know the NN interaction well enough. Today it's the chiral interactions. And so, but the other interactions between the neutron and the proton and the blob nucleus are effective interactions. And there are different options people are doing. It can be purely phenomenological, fit into data. It can be phenomenological with theoretical guidance. In the 90s, the microscopic folding optical potential started, but the goal is still to create these interactions ab initio. And there's a white paper which stems from a workshop 2 years ago here, which is published here. And we had another workshop at ECT Star in 24. So now what you do formally, if you want to project out degrees of freedom, you separate your Hilbert space into P space and Q space, and you compute in P space, and you effectively treat Q space. This is an old insight by Feschbach. And what you get is effective interactions are by definition, if you do that, non-local and energy dependent. And so from this thing and what is often used, people did phenomenological optical potentials. They were always local, fitted to some Wood-Saxon. They were energy dependent. Sometimes they had some Gaussian non-locality, and some of them, if dispersive models are used, you connect from the scattering regime in the imaginary part to the bound state spectrum. So, but basically, there's one thing, you fit cross sections and other observables, and usually the lightest which is used is carbon-12, and sometimes only the phenomenological start at calcium-40 and go to the higher nuclei. So, but now we want to do an ab initio, and basically there are two ways and theoretical foundations that were laid in the 50s. One is by Feshbach and the other one by Watson. The Feshbach has the following idea. You created via Green's functions from a solution of the many-body problem. For example, a coupled cluster, this is Edini, or you use some other methods and extend your bound state method into the scattering regime by extending your model space. I put here, this is an older one from 2017. The symmetry adaptive folks have been very active. Burroughs, Lowney, and Mersenne did neutron scattering on helium-4. This is the total cross-section as function of energy. And our own Grigor has a recent publication where he did neutrons on magnesium-24. So there is one limitation will be in this, that you have to increase your model space, and that gives you de facto an energy limit how far you can go. I mean, you can push the computer, but I'm not so sure. I mean, I'm not the person to say, I put a roughly average 10 MeV. Maybe you can push it to 20, but not that much harder. The other approach is the multiple scattering expansion. For example, the spectator expansion. Watson started it out in the 50s. It was then formulated more crisp by Siciliano and Thaler and Pickelsheimer and Thaler. And so there the basic idea is you expand your scattering problem in active particles or nucleons active in the reaction, and you antisymmetrize in the active particles. In the original paper, Watson said it's multiple scattering for fast neutrons. In the 50s, fast neutrons were, let's say, 60, 100 MeV. And, but basically, going forward from that, you have, the idea is the following, and I sketched this very briefly. I have a backup slide if somebody wants to know more details. But basically, if you want to do elastic scattering, you have to formulate your P space. And for the P space, I project on the ground state. And so my Hilbert space looks, one is P plus Q, where Q contains all excitation, all knockouts and everything. And so for elastic scattering, you sandwich your transition amplitude in with the operator P. While you do that and put the P in, you split your Lippmann-Schwinger amplitude into two pieces. The one which lives in P space, which is the one you compute, and then the optical potential, which lives in Q space, and this is the effective optical potential. This is still an exact expression. Then you have to work in Q space and actually see what are you taking in. And so basically, if you have single scattering, my notation is always projectile is particle number 0, and the ones inside are I's and J's and stuff. So here you have 2 active nucleons. Double scattering, you would have 3 active nucleons and so on. And as one of the kind of tidbits, Watson and Fadeev were contemporaries. So actually you can, if you don't have a nucleus anymore, you can rewrite the double scattering term also in terms of Fadeev amplitudes. And so just so there are not any different theories in that sense. We are leaving only with this one here and expand the operator U. And so if we want to do now a framework for ab initio scattering, what you saw, this is the picture, and I put on purpose the projectile has spin and the nucleons in the nucleus also have spin. So this is the picture. Now, how do you deal with that ab initio? You have this beast here that is the realm of structure people. So, for example, there is a no-Corshell model. Then the scattering, if I do leading order only, that is a reaction theory where you have the spectator expansion, or when you combine it, you can do Green's functions. But the most important point is, if you want to be ab initio means that you take the same NN interaction in all pieces of your problem and don't kind of take one from column A and one from column B. So basically, I put here, this is a picture from Applebaum, Krebs, and Meissner. And basically, this is a two-nucleon force. You are normally used to see that in phase shifts. This is what the structure gives you. We get the Newton matter distribution, how they come out of the calculation. So now let me just say something about the NN interaction. Normally, you are used to the NN interaction, then a bunch of diagrams, you work all the diagrams, you partial wave decompose them, and you compute phase shifts. That is not the most useful thing in this case, because you have one of the nucleons is sitting in free space, namely it's described by a plane wave, and the second nucleon is sitting somewhere inside the nucleus. And I'm writing this here, so it is very good to look at the operator structure of what you have. You can rewrite all NN interactions in terms of the operator structure. And I do it a little bit different than from a textbook here. I have the operator 1 is for one nucleon, and I put always the left one is number 0, and the one here is for the one inside the nucleus. So you have here a 1 operator. This one here, I pulled it apart. Normally, if you have sigma 0 plus sigma I, you would have capital S, spin 1 or spin 0. But I pull them apart here to make clear that there is a spin orbit piece which comes outside and a spin orbit piece which is inside, okay? And then you have, of course, here the projection of the spin along all the momentum axis. I should say I'm living in momentum space and breathe momentum space. So there are characteristic momenta. You have the momentum transfer, the average momentum, and the normal to this. If you write it in this thing, you have A is a central part, C is a spin orbit, and all these 3 other ones are tensor pieces. So for example, if you would have the 1 pion exchange, if you remember the momentum space expression, it has a sigma 1 dot sigma 2 that actually can be decomposed in all of those 3. So you populate these functions here, and you have the tensor operator you also populate here, and you have a counter term in effective field theory, there you populate A. These functions here, they're called Wolfenstein amplitudes. They are scalar functions of complex variables. Okay, so, and that's the most general structure you can have. Now, let's go, what do we have to do if we want to consider the spin inside the nucleus? And so, this is the general expression without the red piece, how you start, yes?
So technical question on the previous page. So those amplitudes, do you have crossing symmetries? Like the nucleons cross, so you have...
there is no, this is, what does cross? Cross is a diagrammatic thing.
So basically antisymmetrization of 2 nuclei in the final state.
The antisymmetrization comes out when you actually calculate the amplitude. For example, I mean, it's, for NN, for NP, all partial waves contribute, whereas for the T equal 1 isospin 1 channel, you have only a selection of amplitudes. That comes in when you actually calculate these functions. That does not affect the operator structure. Okay, so this without the red piece is the general thing, how you start out, for example, calculating a density. To do the spin, we put this one inside here. I put a capital S in here because for two spins, they either can couple to spin equal 0 or to couple to spin equal 1. Spin equals 0, that tensor is 1, and you get the scalar density out. If that S is equal to 1, you have a spin dependence. And so, but densities are scalar functions, so you will have to project this density along all the three momentum vectors. So let's do this one here. I'm just writing, have that in mind. You have reaction information, structure information, and all the things that put it together. And that makes it actually involved. So basically, the potential looks like something here. I have a piece which is here dependent on this on the spin. And at the very end, you have this is coming here. That's a nucleus. It's a diagram. And here's the n amplitude. You will have to integrate over all these internal momenta. That's what it is. It's like calculating a diagram, but with other stuff inside. So let me go back a little bit here and see what is happening now. Again, this I put on here the plane in what momentum vector I have. And so the blue ones are the external ones. And then so I would have to calculate inside the density sigma I dot n hat dot q hat dot kappa hat. So all these scalar products, because the end, this we call this a spin projected momentum density. It has to be a scalar, and we project along. And then you kind of build up the density out of Clebsch-Gordons and stuff like I think like Heiko does the no-Koshel model and so does. And what we actually see that there are three of them. Sigma I dot n hat is the only thing that survives. From symmetry, you can think why it is. Sigma is a pseudoscalar, and hat is a pseudo sigma is a pseudo vector, and hat is a pseudo vector. So pseudo vector times pseudo vector gives a vector, gives a proper scalar product. These two here are not parity invariant, so they disappear if you do this for a spin 0 plus nucleus. And you can, it's analytically clear, we also verified it numerically. So after we have done all of that, I'm just writing the answer. And so what you are getting a non-local momentum space potential, which has, here's always the integral over. I underline here all the amplitudes that show up. And point is, if you do, and you have two different densities, the scalar density here and the spin projected density along n hat. And so what you see also, you have from all pieces of the NN interaction something contributing. The spin amplitude m, which comes actually from the nuclear-nucleon tensor force, shows up in the spin orbit. It is very small. In the very old days, people like to compute only closed shell nuclei, calcium-40, lead-208, and zirconium-90. And the argument was all the spins are lined up so they cancel out to 0. There's a miniature contribution, but this M actually shows up if you have N unequal Z nuclei. Then it actually can make a difference. So for the traditional closed shell, even in the no-Koshel model, that contribution here is relatively small. And you get here to the central part also something which is from the spin orbit, which actually gives you a contribution like to the deformation, if you want to think about physics. And so once we're done with that, and I want to stop formulas now, I wanted to give you some idea that what all enters. And now let me give that insert here for those who are not most familiar with scattering calculations. If you scatter, you have a particle from a target. You have the scattering plane, which is spanned by the momenta p and p prime. And so that is the momentum transfer. And the average momentum lies also in the scattering plane. And you always have the normal to the scattering plane. And so in momentum space, remember the momentum space representation of the spin orbit is sigma dot n hat. And that if you Fourier transform this, turns out to become L dot S. The observables which you have, aside of total cross sections and total reaction cross section, is the differential cross section, the sigma d omega. And you have the analyzing power and the spin rotation function. The analyzing power measures in the experiment, the spin is aligned perpendicular to the scattering plane, and you measure spin up minus spin down over the sum. The spin rotation function comes from if you polarize the beam along the momentum p, you do a scattering, and it doesn't necessarily, the spin changes if you have a spin-dependent interaction. So in the outcome, it will not be naturally aligned with the momentum p prime anymore. And that's why it's rotated away from that. That's where the term rotation function comes. You can already, actually for the experimentalist, it's probably clear to you, if for the spin rotation, you have to do a double polarization experiment because you have to detect the polarization. You have to polarize before, and you have to detect polarization afterwards. That's why the measuring Q is difficult. There are not many Q data, and I think for radioactive beams, AY has been measured at weaken. Q is probably out of the question. So after that insert to get everybody on the page what we are actually looking at, now let's look at stuff. And so the first thing is, I mean, this is still from Matt Burris' thesis. We did closed shell nuclei. And we did in the thing helium-4, 200 MeV, 100 MeV, and differential cross-section, always divided by Rutherford to actually see how you do in forward direction. And this is the analyzing power. And we did it here for oxygen. And so one of the things where I thought was a figure of pride was, if you look in forward direction, that gives you the strength of the interaction. And without parameters, without Initio, the forward direction, we get the strength here in the cross-section correct, which I think that is an achievement. Here, I mean, it's okay, at 200, the observables are better. You see here for the closed shell, it's not that great. Or you see deviations. Now,
May I ask a question? Do you actually use a closed shell wave function?
we are using whatever Peter Maris gives me out.
Because they're mixed. In other words, it's in the theory they're not 100% closed.
They're not.
They're only like 80% or something.
Peter Maris says, I mean, helium-4 is relatively close.
Yeah.
Oxygen, he says, that's why the convergence pattern, he has to go here at Nmax 10. And so
Okay.
there's a lot of oxygen. We are using everything which comes in.
Right.
Okay. So now, then we also did the open shell. And for open shell at the time, it was really helium-6 and helium-8. These were the nuclei of interest from RIKEN because, I mean, here, differential cross-section, and we also did carbon because Christina Launi loves carbon. And so, but let's have a look at this one here. 200 MeV, there were data. It's amazing. It's good. There are no data. I think there are data, but they have never been analyzed. This is carbon at 200. And then the helium experiments at RIKEN were done at 71 MeV. So we computed at 71 MeV. And it's actually amazing. There are two different data sets where they measured the overlapping stuff that they are okay. So this is helium-6, this is helium-8. We found this amazing. And specifically that for the higher Q, it works much better than for carbon-2. Okay. We went then on with Christina and Robert Baker to push to heavier nuclei. And I want to show here just two things. I mean, we did neon-20. And we wanted to push at the time towards calcium-40. I mean, that was the thing. You always want to push your technology and see if it goes. Again, what we see, and I'll come back to that later, neon-20, the cross-section is not bad. It's only 65 because for neon-20, they're only data at 65 MeV from Osaka. Data where you also have an AY. If you look at this one here, you see something that though the minima are pretty much here at the beginning at the right point. Observables, it's okay, and even the observable Q, which for calcium is measured so well, is there. We get the correct diffraction pattern. Okay. Then we did a bunch of calcium because calcium is so well measured, and we see the following. Yes, the diffraction pattern is too deep, and when we go higher, it moves slightly over. That must have to do something with scattering because densities are definitely not energy dependent. The spin-up level, the AY, is actually described pretty well for a ab initio without fitting anything. Okay, what is this? My comment to this is from if you do Fadeev calculations, which I also have done, and the Fadeev series is also a multiple scattering series. So the leading order Fadeev is also too deep in the minima, and only rescattering actually fills up the minima. So that's, I think, what we are seeing here. But there's one observation which I want to go back to. We found that for helium, even up to higher momentum transfer, the data are described quite well at the low energy. For neon, it's also not that bad. It's certainly better than for calcium. So what is the difference between those nuclei? We have helium is a halo. Neon is a cluster state. Calcium-40 is a very densely packed system. And so it could very well be, and so if we're doing leading order and omit the rescattering. So it could very well be that for a clustered system, deformed system, the leading order is much better than its reputation just because rescattering terms are suppressed. We have 3 data points. Should make a theory with 3 data points. So that's why I'm here. I have a project with Grigor. Grigor is calculating magnesium-24 and magnesium-26. Magnesium-24 has data at 65 MeV, also from Osaka. Magnesium-26 has not been put in a target. I talked with Alexandra Garde, and she thought maybe it's because it's too expensive. At some point, I'm never worried about how much it costs to put a target together. But that's what she thinks could be. And we want to push towards titanium.
If you go back 2 slides, the radius is not so good for calcium. Down in the lower
Yes.
corner.
It's also.
Doesn't bother you?
Okay. Calcium is not very well converged. If you look, it's because, this is something Robert did. It's H bar omega 12, no, I think 11, 12, and 13. Okay. Peter Maris can calculate now calcium-40 at Nmax 6, and he did a whole slew of H bar omegas. The radius depends tremendously on the H bar omega. So, and the energy. And so there is, for the no-Koshal model, what Peter Maris has to do, there's an energy conversion and there is a radius conversion. The energy of calcium-40 is much better for the large H bar omega. The radius is catastrophically small. And so for the smaller H bar omegas, the radius is much better. And so it is small. It should be, I can go even, I think this was from the no-Koshal, from the symmetry adapted. Peter Maris is not at the experimental. You have to go to H bar omega 10, where you get roughly to 3.3. So the calculations are very much H bar omega dependent. Because the model space.
I wasn't saying that so much, but aren't you worried that maybe since the radius is not right, then your other things,
that is the diffraction pattern gives you an indication if your radius is okay.
Right, but your radius is wrong and your diffraction pattern is not bad.
Okay, let me just say something. You see here, the diffraction pattern is not okay.
Okay, that's
the point. There was another calculation by Matteo Vorabi, who used a density from Green's function and stuff, self-consistent Green's function. And he got that point correct. And then but his low energy radius is off. So the mystery why the diffraction pattern is shifting is not solved, because that cannot be the density. And so, there is, I mean, it's two different calculations. We are okay here and off here. He is okay here and off here. And the shift is the same direction. There are only two of these ab initio calculations at the moment available. Okay, let's go here. So this is our project which we are doing. And we prepared all the codes and stuff that Grigor can work on that. Let me kind of summarize up to now what we did. We can do it. We can, if we really construct the density from scratch with spin, the spin projectile can be included. It's being explored. We're trying to push. And so some indication is that the leading order is better for clustered nuclei. That has actually an advantage for if you want to go in the area of exotic nuclei, that we can compute something, and this computation can be taken as pseudo data if one wants to fit phenomenological potentials. That's why I'm so keen with Grigor to figure out if that is a consistent trend. So that's where we play with, and I think that could be very useful for the community in a sense. Now, since I'm here and I have been asked already about error analysis, let's do error analysis. We have done it, okay? And so basically we did the Buckeye approach, that you rewrite your observables as some reference state and an expansion in an expansion parameter Q. We chose this one here. This is a relativistic momentum. This is kind of that cheat sheet. And basically it's a work mostly done by Robert Baker and the assistant of a student of mine. Uncorrelated, this is the reaction cross-section for oxygen. And so basically the 68% confidence interval is this. And this was the H bar omega band from 16 to 28. And so the confidence interval is bigger than the H bar omega error. There's one point, I mean, I think this is the most important part, which I found a little bit disheartening in looking at nuclei, because if you take the momentum expansion as we did in the cheat sheet, you see that because in this formula there is an M in there. So the momentum, the expansion parameter gets big very quickly. So 65, it's 0.5. At 180, you are already at 94. And so it's pretty much not converging. So in the traditional work, I mean, we just did and applied the entire scheme. This was, I think, we found is the sickness. Otherwise, we did then the correlated uncertainty quantification. I don't want to kind of, and we actually put here an X and a P in, and the momentum transfer in our breakdown scale. We just do predictions, coefficients, fit with Gaussian process, and produce error bars. That is the answer. And so basically, and I always put here the Q in, this is LO, NLO, and 2LO. And so what you see here, yes, and we did 6,500 and 180. Basically, yes, you see at 65 with a 0.55, the error bars get smaller. And here, yes, the description is within the data. Here it's a little bit, it's in one of the confidence intervals. It's on the bottom part. So, but if you go to very high energies, it just doesn't converge very quickly. We did something inconsistently here because one of the points is these calculations are pretty expensive, because what we did here is if you do LO, the density is calculated in leading order, folded with the interaction in leading order. So there is every single time, it's a new calculation of the Hamiltonian, the density, plus the interaction. We decided, let's do it one time and see what the answer is. But we weren't so happy with it.
I missed what Q means. What's the physics of Q?
That is the expansion parameter. And kind of traditionally it's either the maximum of the momentum, pion mass over lambda b. We never take that. And so it is a momentum scale which you expand over. And this is kind of the traditional for the correlated. We also took the momentum transfer in the reaction with it. So, and then you just go, it's a scheme to see if the series which you have, if it behaves like a normal EFT should do, that every expansion should get smaller and smaller the higher you go. And obviously this choice is it's normally a good one. For nuclear, it works perfectly well. For the 3-nucleon problem, it also works perfectly well. But we saw this one here, since there's a nuclear mass in, actually the Q gets kind of large. So one could think, do a different Q. We did not want to go spend so much time on this. So we just did what everybody in the nuclear and 3-nucleon sector did. We applied this just to proton-nuclear scattering. And so these are the answers. We went in, if you go, this is at 100 MeV. If you go higher, up to here, the calculations are totally consistent. So LO density with LO interaction, NLO density with NLO interaction, N2LO density with N2LO interaction. And then because here in the N3LO, you need to, in the density 3 nucleon forces, we just stopped the calculation for the density and added only in the NN interaction higher orders to see if at least what people see in the NN, if you go higher and higher, the error bars get smaller. Yes, they do, but it's very slow. And so from that point of view, yes, we did it. We also looked at the posteriors, and they are, it's the value and the map value, they are kind of reasonable. So that's, that actually tests if your momentum choice is reasonable. So we got that one out. And so we left it with that. We wanted to ask also another physics question while we are doing all of that. Namely, if you do neutron scattering, you can look in the dead forward direction of the cross-section. And this is an experiment which was done at Los Alamos. And this is neutron scattering on carbon-12 at 95 MeV. And so I wanted to understand if the forward direction in neutron scattering is highly correlated with the NN interaction. And so we did the same thing. Since we had kind of the calculations done, we did here leading order next to leading order and 2LO and 3LO. And we did here, this is in a gray line I had to put here for CD1, but this is basically, it converges relatively quickly in forward direction. Then this one here is extracted from the NN interaction, the central part, the real square plus imaginary square that enters in a cross section. And it's again, the NN interaction, leading order next to leading order, N2LO, and then kind of everything converges. And then we did basically a correlation, and we can correlate now this quantity with this quantity. And if you normalize it, you see that for every single interaction, the neutron differential cross-section in forward direction goes exactly with the NN interaction, which if you really want to, if you want to get some information about an NN interaction, at least most of, and in forward directions, mostly the central part, you can look at that. And there are some, for carbon, there are some observables from older Los Alamos data. And that is what I found. This one actually, if you look at basically roughly here a momentum transfer up to 1 inverse Fermi or so, or smaller than a half, that there is the very strong linear correlation between forward direction neutron scattering and the strength of the NN interaction. And I mean, you have to do neutron scattering for that not to be clouded by Coulomb. So that was a good thing I found out for that. And so we are coming, I mean, it's, I would say 40 minutes, 45. So basically, we did the order by order convergence, but it was less appealing than something else I did later with the Wolfenstein amplitudes in the two-body system, because expansion parameters are so big. Then at the moment, I'm applying model reduction techniques to off-shell densities as well as the off-shell potential. I have 2 backup slides if you want to know it. It's getting too confused if I put this in, but we can discuss it. But this one here is for me also something to bridge to older codes or other calculations. I think I convinced you the entire scheme of actually getting from scratch ab initio the optical potential is pretty involved. Here in the place Grigor is initiated now. How to do that? I mean, it's a bunch of calculations which have to be done subsequently until you're done. So this is maybe not something which everybody wants to do. So you could think about what is the essence of these either ab initio densities or ab initio optical potentials. Can you use techniques which I just learned because I did some emulators? So there, can we use that technique and see if there are dominant contributions which can be taken out and then maybe used in such a form, either for emulating or checking out, or to make a connection to codes which exist. Okay, because that is the thing you don't want to, I mean, there is a whole body of work of reaction codes. They mostly take local, some of non-local in our space. So if you can have a simpler version of stuff and can refit, you could try something like this. So this could, and the other thing here, definitely, either if we make it simple, you can pave the way so that ab initio information gets fed into reaction codes for inelastic scattering or charge exchange. Or, I mean, but we need to figure out the same things for transition potentials. So this is kind of the future, and I think I should stop. It's 1:45, and you can ask questions.
Okay. Any questions for Charlotte? Dean, please.
It's not great and clearly explained and interesting. So I wanted to get more intuition for what we see. You say you're momentum space person, but let's suppose I Fourier transform with respect to transfer momentum Q. If this was electron scattering, I would basically get charge densities, right? So one could imagine sort of doing this as well.
There is charged in, I mean, it's basically the diagonal density is a form factor.
Yeah.
We only normalize it to something
Sure.
else.
Yeah, but my question is, if I look at this as a function of energy, center of mass energy, 100 MeV, 50 MeV, what exactly, the different shapes that I see in the cross-section, how do I understand, is that telling me more about the nucleon-nucleon interaction as a function of density, or is it also mixing in some feature of nuclear structure as well?
What it actually does, I mean, it's the fully off-shell surface is relatively energy independent. But you have also an on-shell condition because in momentum space, it's the p square is equal p prime square is equal p0 square. And so in variables momentum transfer and kappa, this gives you an ellipse. And that ellipse glides on that surface. That's where you test off actually the scattering tests of that surface different places.
So for example, if you had the plot of the diffraction pattern with the first diffraction minimum shifting as a function of energy, what, like, does that mean
I
something?
have not understood this. I'm surprised to have, I mean, it's
Yeah.
that the older calculations didn't give that, so I'm not sure what is happening in there. If there is something subtle still in the calculation, since it's only two people who said this, and I didn't have enough time to look at
Okay.
that.
Interesting.
I mean, what is interesting in the, okay, so I actually did backup slides in there. That is from the recent paper which we did, where we just did the SVD decomposition of the densities. And we found out that, okay, so this is a typical thing. This is SVD in pictures. You have the diagonal here, and you have your left and your right. For square one, you can define a preserved variance and then a tolerance. So what we did here is basically for all different N maxes, different H bar omegas, basically the how many significant sigmas do you get per nucleus? And basically, and everything which is below the tolerance is basically irrelevant then. So helium-4 to oxygen-16 is roughly, you have two dominant, so it would be a rank 2. Calcium-40 is a rank 3. And so we did the same thing for open shell nuclei. And so Peter Maris tortured, I mean, for some of these things, he needed all of NERSC or all of argon to do the calculations. But the point is it's very systematic, and it doesn't even depend on the end interaction. So that was interesting. So now we are doing the same thing for the optical potentials. SVD works for complex function as well as for real functions. We have now a central piece and a spin orbit piece, and this is the first one. My student Jose, who is second here, he started doing that. And this is oxygen-16, the central, and the spin orbit as function of energy from 65 to 200. We just calculate and say 65, 100, 150, 200. And what you actually see, these singular values are not energy dependent. I was floored when I saw that, okay? So that means, on the other hand, all the energy dependence will have to be in the vectors. And so we have to understand the vectors a little bit better. And so basically, same as for the spin orbit, I put here that tolerance line is not fixed in stone yet, because it's actually much easier to do it in for the scattering, because we have the full calculation. Then he does a rank 1 approximation, see how good it describes your verbals, calculates the error, then rank 2, and then rank 3. It turns out for the spin orbit, it looks as if you need rank 3. That depends on the energy. Okay, he did the same for calcium, and I was even more floored because calcium looks like oxygen. Well, it's okay. Maybe we are doing now, right now, it's closed shell. Maybe there's a difference because we also wanted to do then carbon 12 and neon 20 or something. So maybe there is a difference. Do you work with closed shell and open shell? So this SVD, I mean, it is math, but I think the point in the SVD is the computer tells me something, and I may be slow in understanding what the computer tells me. I mean, actually what systematics we are finding. But the point is, I mean, Philomena got really excited about this because supposedly you have a rank 2 or rank 3 optical potential separable. The separable functions are easily Fourier transformed to R space. And so you can also have then the function of the variable R prime plus R over 2, what would be the local one, and you have a non-local. She's interested on the form of the non-local. Yes, okay. I'm interested in is asking the question, SVD is supposed to filter out from any kind of function you give the most important contribution. Is that true? If we Fourier transform that, to what error do we get the first thing? If we get the vectors, that could be something, could you train something on these vectors? So there is a bunch of interesting questions to be asked. I mean, in Philomena's group, Jose is coming in the first week of December. And I mean, he's not giving a seminar. A second-year student doesn't have to do that. But he put some slides together and with stuff. And I know Philomena, in our group, we will see what he has done by then. Okay? Any more?
Kyle.
So you've quantified the uncertainty of the truncation of the NN interaction and of H bar omega in the structure calculation. What's the uncertainty of the spectator expansion taken to leading order?
There is a problem that you don't know the expansion parameter. I mean, it's you expand in the active particles. That is not a number in sense. And so far, nobody has really calculated the second order. We have done a piece of it from the propagator and found out that above 100 MeV, it's totally irrelevant. And so what we are thinking, since we're also, you could do a following thing. You could do like a missing error or discrepancy model and kind of start out where the data are pretty well described and then kind of see how errors develop as function. And that could give you an idea how big a correction would have to be if you compute it.
In principle, the result of the NCSM calculation should give you the full ground state wave function. So you should be able to get a two-body density out of that, no?
Yes, but it is more. I mean, it's basically what I'm thinking of, and I talked with my first postdoc advisor, Peter Tenney, about it. I think it is out of the question and maybe really too involved for a little bit to get out, do a full Faddeev calculation in the medium. What he advised me to do, look at what people did in the 60s at approximations to Faddeev equations and actually peel out the most important part.
Yeah.
I think that's probably the smarter way of going about it.
But if you got a SVD on the two-body densities and it also had low rank structure, that might be really interesting.
I mean, there is a lot of stuff. I mean, it's okay. I mean, I got into this with thanks to Streamline into that, and I think you can apply this stuff to other things and actually see what are the important pieces. And I mean, it's a very different way of looking at things, but it's also a thing to see what are the important pieces and to what accuracy do you want to have it? Because now you can ask a question. I mean, it's if you want to have a reproduction of a scattering observable, maybe with 10%. Some people may be happy with 10%. If you want a next order, how much do you get? Here with this one, we did not do an error analysis for the densities because if two singular values are enough, that's not, you have only two. But here, if you need to do more and more, we can actually do an error analysis. How much do you have? I mean, it's how fast do you converge to the correct value? And then you could ask also at some point a question, how fast do you converge to experimental data and look at those two differences? Because there will be a theory error and kind of like a methodology error.
Okay, there's a question.
There's one more.
In chat.
Oh.
Okay, yeah, she'll go ahead.
Yeah, on
Then
this
I will.
So in the dispersive optic potential approach, do they have these kind of structures like spectator expansion in the dispersive?
No, the dispersive is basically in the imaginary part. I mean, you have to do something. The imaginary part should go to zero.
But they also do the diagram calculation. There's a diagram summation.
Well,
It's phenomenological.
but it's phenomenological.
But they have this self-consistent Green's function method.
Yeah, but the actual.
That is
Well,
not, that's different. I mean, I think maybe there is a misunderstanding. I mean, it's if you do this, the Green's function like Grigor does, he actually computes everything. Well, I think what you're referring to Wim Dikhoff.
Yeah.
I mean, he calculates the like in Hartree-Fock the states and makes sure that when he kind of does the integral over the imaginary part, that he actually gets his states in the HFB correct. But then the rest for the scattering part, it's phenomenological.
Okay, I'm gonna try to
Oh.
ask this question before we run out of time. So Chloe says, thank you for the talk, and she's asking how accurate are the binding energies of ab initio calculations, and is it within a few percent or more compared to experiments?
Okay, I mean, I'm not the right person to answer that question. I have to look at the outputs. Basically, if you go converged, Peter Mays, they actually have a bunch of papers on that for the light nuclei where they go to Nmax 1820, they converge and it's relatively good. Then if you go to the heavier one, it's not converged. So you have the H bar omega dependence and you have to put that error bar on.
Do these binding energies enter in your calculations in any way? Okay. Any other questions?
That's the difficulty to include the three-body force in your effective detection.
In the spectator expansion leading order, there is no three-body force.
Yeah, but since the no shell model which you showed before is all of them, they are using NNLO opt, which means three-body effect is a kind of small, I believe. So I'm thinking if you can have you tried to other interaction with, for example, the magic interaction or something else?
Magic, I think maybe 8 years ago, we did one calculation, calcium with magic. And it was okay, but I didn't continue work on it. We do the Dijon, and the order by order was actually done with the Lenpig SCS with a cutoff of 1 Fermi. There you have to do the full chiral interaction. And since Peter Maris is also in the Lenpig collaboration, I took the Lenpig. There's and so that answers your question. What happens, amazingly enough, N2LO opt is really good in describing data even at higher energies. Could be because of that. But I think magic is more for calcium and higher.
Okay, maybe one last quick question. We have 1 more minute, if there are any. Sure, Kyle. Wait.
Anyone else? Going back to the diffraction pattern, the location of the first diffraction pattern is a function of energy. The data also follows that trend, right? It should. Yeah, it does.
Well, okay. What do you mean? The data is, I mean, yes, it goes a little bit forward, and we have the opposite trend. So, okay, I do here, I cut off here, angle is, I don't know if it's exactly the same momentum transfer. Because, I cut this off here on the top, there should be a momentum transfer. But it looks here, if you look at angle, this is here 20 and it's a little bit less than 20.
It seems like the model is not shifting far enough, right? The model is shifting back, but just not as far as the data shifts back, right? Yeah.
And for those, I think the data are very likely very accurate because it's calcium.
Okay, good. On top of the hour. Thank you, everyone. Thanks.
And I think